in Chapter 5, Integration. Section 5.1 is Indefinite Integration and Differential Equations. Derivatives provide information on rates of change and allow us to find extrema of functions. It is not always possible to find a ready-made function that provides information about a total amount of a quantity, but it is often possible to collect enough data to come up with a function that gives us a rate of change of a quantity. The reverse of finding a derivative is known as anti-differentiation. So, for example, if f of x equals 7x, then the derivative of that is 7. So f of x equals 7x is an antiderivative of our original function, which is just f of x equals 7. So next example says if f of x equals x to the third, then the derivative would be 3x squared. So f of x equals x to the third is an antiderivative of f of x equals 3x squared. All antiderivatives of a function f are of the form, you'll see this symbol, it looks almost like a little snake. That's an integral symbol. F of x dx equals f of x plus c. So where that symbol is the integral sign, f of x is the integrand, what you're integrating, and the integral of f of x dx is called an indefinite integral. Also, the dx here tells you what to integrate with respect to. Just like when we were taking derivatives, we would sometimes take the derivative with respect to x or with respect to y. This is telling us how to integrate or take the antiderivative of the function. So an indefinite integral is where f prime of x equals f of x, and the integral of f of x dx equals f of x plus c for any real number c. Then down below we have rules for integrating common functions. First one is going to be the constant rule. So k is a constant, and the integral of k dx is kx plus c. You'll notice this c is on here, which is just a constant. So c is a constant. And you can always check these by taking the derivative of your answer. So you can check this by taking the derivative. And the derivative of kx plus c would be the derivative of kx would just be k, and the derivative of constant c would just be 0. And so we would get that integrand, what we were looking at originally and taking the integral of, which was just k dx. Our power rule, we remember, was taking our exponent for taking a derivative, moving it in front of our variable and subtracting 1 from our exponent. So now we're going to be doing the opposite of this. And so we have x to the n dx. Taking the derivative of this is going to be x to the n plus 1 divided by n plus 1 plus c. Some students find it a little easier to think about the formula as 1 over n plus 1 times x to the n plus 1 plus c, our constant. Then we have our natural logarithmic rule, which is the integral of 1 over x dx, which is equal to ln of, and don't forget your absolute value lines that are on here, of x plus c, so x is not allowed to be 0. Another way to think about our original integral function here is the same thing as the integral of x to the negative first dx, which is the same thing as the integral of 1 over x dx. And then our natural exponent rule, which is going to be the integral of e to the kx dx, is equal to 1 over k e to the kx plus c, and k is not allowed to be 0. So right below this we have an example. The example says find each indefinite integral, and so the first one that we have is the integral of x to the second dx. And so to do this, what we're going to do is divide by 1 over 2 plus 1, and I am going to write this out a little bit more using our power rule. And then x to the 2 plus 1 power, and then plus our constant. So 1 over 3 x to the third plus c. And just so we know, we can check this by taking a derivative. And so we have 1/3 times 3x to the second plus 0. And that would simplify to just x to the second, so check. Likewise for b, we have the integral of 1 over t to the third dt. And I'm going to go ahead and rewrite this as t to the negative third dt, so I can use that power rule. So the power rule is adding 1 to that exponent and dividing by it, so 1 over. And then our exponent is also going to be adding 1 to that too, and then plus c. And so we end up with negative 1 over 2 t to the negative second plus c. For part c, I'm going to rewrite this as the integral of x to the 1/2 dx. And some fractions here, and just go step by step slowly, but with our power rule, it's going to be 1 over our exponent plus 1, x to the exponent plus 1 also plus c. And so this will work out to being 1/2 plus 1 is going to be 3 over 2. So we have 1 over 3 over 2, x to the 3 over 2 plus c. And then 1 over 3 over 2 is just going to be the reciprocal. So we get 2/3 x to 3 over 2 plus c. And again, you could take the derivative of this to check to see if you did it correctly. You should also rewrite it, since this was written as a root, 2/3, and we have the square root of x cubed plus c. The last one that we have on this page is the integral of du. There's nothing there, so technically it's the integral of 1 du. And so if you think about this as the integral of u to the 0 power, or just 1 as a constant, so we're going to take 1 over our exponent plus 1, u to our exponent plus 1 also, plus c. And so this is going to work out to being 1 over 1, or just 1, u to the first plus c. We have 2 more on the next page. So I'm going to go ahead and circle E, and we'll look at that one together in class. For f, we have the integral of e to the 3x plus 1 over x dx. And so taking the integral of e to the 3x is going to be 1 over that exponent, the constant part of it, which is 3, e to the 3x. 1 over x, the integral of that is going to be ln of the absolute value of x. And then we also have a plus c. Again, you can take a derivative of your answer just to check to make sure that you did it correctly. Next thing down below is algebraic rules for indefinite integration. Let k be a constant. Then we have the constant multiple rule, which just says that if you're multiplying by a constant, you can pull that constant out in front, kind of like what we just did with taking derivatives. And then sum and difference is going to be taking the integral of each term individually. So we have some examples right below. And the first example says find each integral, and we have the integral of 5 times t to the 4th dt. And so you can think about this as just 5 times the integral of t to the 4th dt. And so integrating this, the 5 would stay there, adding 1 to my exponent and putting that in the denominator, and adding 1 to the exponent that we have now, plus c. This would simplify to just t to the 5th plus c. B, I'm going to rewrite a little bit before integrating, which is going to be the integral, and I could put the 3 out in front, and we have u to the negative 5th du. So taking the integral of this, we have the 3, which is a constant. 1 over negative 5 plus 1 is negative 4, u to the negative 4th power plus c. This would simplify to negative 3/4, moving that u to the bottom, positive 4th plus c. Part C says the integral of 4x squared minus 5x plus 3 dx. So we're able to take the integral of each of these terms individually, so that 4 would just stay there. Integrating x to the second, I would add 1 to the exponent and divide by that value. X to that same exponent, minus 5 times x to the, this is to the first, so adding 1 to that would be 2, so 1 over 2 x to the second, plus 3, which would just be 3x, plus our constant c. Just cleaning this up a little bit, we get 4/3 x to the third minus 5 over 2 x squared plus 3x plus c. Then we have part D, which I'm going to go ahead and circle, and we'll look at this one together in class. Right below this, it says indefinite integrals of additional exponential functions. So definitely something we should know. It's going to be for a greater than 0 and not equal to 1. The integral of a to the x dx is equal to a to the x over ln of a plus c. And then the integral of a to the kx dx is equal to a to the kx over k times ln of a plus c, where k is not allowed to equal 0. The example at the top of the next page says find each integral. So it says the integral of 5e to the x plus 6 over x dx. So integrating this, we're going to end up with 5. The integral of e to the x is just e to the x plus 6 times, and the integral of 1 over x is ln absolute value of x plus our c, our constant value. Part B says the integral of 3e to the 4t dt. And so for this, what we're going to have is 3, which is our constant, times, and we have 1 over 4 e to the 4t plus c. And so rewriting this, we can have 3/4 e to the 4t plus c. Part C says the integral of 2 to the negative 4u du power. I'm going to use those formulas that are at the very bottom of the previous page. You can see them right now. And so this is going to be equal to, and so it's going to stay 2 to the negative 4u over negative 4 ln of 2 plus c. So again, looking at that bottom equation that we had on the previous page, it is 2 to the negative 4, which is our k value, and then we have u instead of x. D, I'm going to go ahead and circle, and we'll look at that one together in class. Remember, marginal cost, revenue, or profit is the derivative of the cost, revenue, or profit functions, and if the derivative of the cost function c of x is c prime of x, this would imply that the integral of our derivative c prime of x dx would be equal to our cost function. So, example right below this says find the cost function from the given marginal cost function, which is c prime of x equals 0.2 x to the second plus 5x. Fixed cost is equal to $10, and we'll talk about what that means in just a sec. So what we have is we have the integral of our marginal cost function integrating with respect to x, which is equal to c of x plus c, that constant term that we would have. So we're going to be integrating 0.2 x squared plus 5x with respect to x, and when we integrate this, we get our constant, which is 0.2, times 1 over 3 x to the third plus 5 times 1 over 2 x squared plus c, that constant value that we have. Simplifying this a little bit, 0.2 divided by 3 simplifies to 1 over 15 x to the third plus 5 over 2 x squared plus c, which is our constant. So it also tells us that this is our cost function, but we need to take into consideration that our fixed cost is equal to $10. Fixed cost is what doesn't change if we have sold a certain amount of products. So this would be what we would always have as a cost, even if we sell no products. So this is going to be the cost when selling x equals 0 products. So in order to figure out what the c value is, our cost, our fixed cost here, and our cost function would be 10, is equal to 1 over 15 times 0 cubed plus 5 over 2 times 0 squared plus c. And so working this out, we get c is equal to 10. And so our cost function is going to be 1 over 15 x cubed plus 5 over 2x squared plus 10. So right below this, we have another example that I'm going to circle, and we'll look at this one together in class.